Okay, so let's go. So welcome everyone to the WEAMEC webinar. So as I said at the beginning, so that one is going to be in English for an international attendance, and also because the ColFOWT project that is going to be presented by Hervé Le Sourn has been funded by our WEAMEC international project call, aiming at having a collaboration between an overseas entities, and here you will see two ones collaborating in the project, NTNU and Liège University, and the ICAM Institute from Nantes, and a member of the WEAMEC community. So this webinar about the ColFOWT project is going to be of a duration of about 1 hour. So we are here on the webinar participation, so you can interact on Zoom during the webinar. So for all of you, your camera and microphone are muted, but you can interact and use the Q&A button. So Q&A for English, Q&A is, or it is written for the French version. So you can ask your questions there, and we'll answer them as most as we can at the end of the presentation. And for you to know, so this webinar is recording for broadcast on our YouTube channel, and where you can also find our last webinar. So all the webinars are in our WEAMEC YouTube channel, where you can find different webinars about general presentation of the WEAMEC community and ecosystem, but also about our research calls for projects, and a couple of ones about our research projects. So, and this is, we are happy today to have our 15th webinar, and the first one to be in English. So today we are here together for the ColFOWT project. So I will just briefly present you here to the context. So the objective is to develop a rapid simulation tool for the analysis of ship and floating offshore wind turbine collisions. So this is led by Hervé Le Sourn, that is going to present you the project and the results. So he is from the ICAM Engineering School, and this is a collaboration with different partners you can see on the screens. So please, Hervé, you can share your screen and start your presentation, and please introduce yourself.
Okay, so do you see my screen? Is it okay?
Yes, perfect.
All right. Good afternoon, ladies and gentlemen. Okay, so my name is Hervé Le Sourn. I am professor at ICAM Engineering School in Nantes and researcher at GEM Institute. So I will present this project, which name is a ColFOWT research project, which has been carried out within the framework of the WEAMEC community, with fundings from Pays de la Loire region, European Regional Development, and ICAM Engineering Schools. In fact, ColFOWT, as you see, means collision against floating offshore wind turbines. This project should be placed in the context of a risk-based analysis of floating offshore wind farms. In fact, the probability of a vessel colliding during an avoidance maneuver by another vessel or drifting due to a propulsion failure is not negligible. So the consequences can be significant. For example, one consequence could be the collapse of the wind turbine tower falling on the ship weather deck, or damage on the wind turbine generator due to high accelerations of the nacelle, or rupture of the onshore lines, and in the worst case, loss of human life. Collision risk analysis is usually quantified by the probability of occurrence of a breach after collision, multiplied by the consequence, which is characterized by a measure of the breach. Of course, finite element analysis may be used to quantify the severity of the damage, but it's well known that explicit finite element simulations are often very time consuming and require a lot of expertise. In this context, stakeholders of offshore wind farm industry, like design offices, classification societies, yards, and also regulation authorities, need a fast and reliable tool that will allow to identify quickly the consequences of a ship collision, to improve the crashworthiness of the wind turbine, but also the ship bow, to simulate numerous ship collision scenarios needed for risk-based analysis, and also to define appropriate precautionary and compensating measures for maritime traffic. Regarding the originality of the project with respect to the state of the art, I can say that the fast design tools have already been developed for ship-ship collisions or ship fixed offshore platform collisions. But here in the ColFOWT project, we propose to develop a tool for collision against floating structures, including the action of hydrodynamic forces, mooring lines, and wind. The project will consider both metallic spar-light floaters and reinforced concrete floaters. In a scientific point of view, it was proposed in this project first to develop new superelements to simulate the shock elastic plastic response of long cylindrical structures with a mass at extremity, the shock of elastic plastic response of reinforced concrete slabs on the concrete floaters. And second, to couple the superelement solver with an external dynamic solver able to simulate the action of the hydrodynamic forces. Developing a fast, reliable, and easy to use tool will allow the design offices to conduct complete collision risk analysis, because this analysis, in fact, involve hundreds or even thousands of collision scenarios, which are obtained by varying the striking ship, the impact velocity, the impact location, the impact angles, etc. So the idea is just to develop a semi-analytical solver, which is based on closed form expression derived from plastic limit analysis. And these analytical expressions will give the resistant force of macro elements as well as dissipated energy as a function of the penetration of the ship into the structure. So the solver developed in ColFOWT project, in fact, is similar to the solver SHARP, which has been developed in France by ICAM Engineering School, Principia, Naval Group, and Bureau Veritas for ship-ship collision. As you can see on this slide, the ColFOWT project is realized in strong collaboration with University of Liège, University of Trondheim in Norway, and Central Nantes Engineering School in Nantes. 5 work packages constitute the project. First, new superelements for spar-light floating offshore wind turbines are developed in work package 1. Work package 2 includes drop tests on reinforced concrete beams to validate the simulations. All the expressions developed in work package 1, but also in University of Liège for concrete floaters are implemented in a unique solver in work package 3. And this structural solver is coupled to an existing free solver in work package 4. And finally, numerical simulations are performed in work package 5 to validate all the analytical developments. At the beginning of the ColFOWT project, we performed LS Dyna MCOL finite element simulations in order to identify the main deformation mechanism. Here, we can see a spar wind turbine, which is impacted by a 5,000 tons offshore supply vessel. And these finite element simulations show that the mass of the rotor nacelle assembly, the mass of the ballast, and the action of hydrodynamic forces play an important role in the response of the floating wind turbine. It was also observed in the simulations that this response is composed of local crushing of the impacted section, global beam plastic bending, and local buckling just above the ballast. The successive deformation modes are illustrated here. So we have the local crushing, global bending with plastic hinges, rotation of the tower around the lowest plastic hinge, and finally local buckling at the rear part of the structure just above the ballast. For each deformation mode, analytical expressions have been derived or taken from previous research projects performed by ICAM and University of Liège. And combining the 4 deformation mechanisms, we can obtain from analytical expressions the evolution of the resistant force as a function of the penetration of the ship into the floating structure. In the frame of a PhD thesis, all aforementioned analytical development have been implemented in a solver and confronted to finite element simulations. Here, a wind turbine is collided by a rigid offshore supply vessel at 10 knots, and the force penetration curves are compared in the upper graph, while the energy penetration curves are compared in the lower graph. The orange curve is the energy absorbed by deformation of the wind turbine, while the blue curve is the kinetic energy of the striking ship. So you can see that here, a quite good correlation is observed between analytical and numerical results. When the initial velocity of the ship is lower, here 4 knots, the model developed in ColFOWT project overestimates the resistant force, and as a consequence, the energy dissipated by deformation is also overestimated by the analytical model. So this is due to the fact that for low energy impacts, the elastic response of the tower cannot be neglected anymore. And thus, the local elastic response of the impacted section must be considered. So we are developing now the elastic response, and we are implementing the elastic response in the solver. Okay, so now, just after the collision, we know that an elastic shock wave propagates through the structure up to the nacelle. And so the issue is to estimate the level of acceleration at the center of gravity of the nacelle. And to do this, we base our developments on the multiple discontinuity beam approach, which was proposed by Stanton in 2010. So the idea is to split the wind turbine into large beam components, and the method consists in deriving transfer matrices for each component. The transfer matrices are calculated, in fact, from exact solutions of Euler-Bernoulli beam movement equations. Then we combine appropriately the transfer matrices and we obtain an eigensystem, which is solved to obtain the natural frequencies and mode shapes of the beam assembly, but all this without having to mesh the structure. Here, for example, we consider a monopile, which is fixed at its lower extremity and supports a mass of 350 tons at its upper extremity. And you can see that natural frequencies and mode shapes are calculated using the multiple beam discontinuity method. Then the shock response of the overall wind turbine is calculated by a modal superposition approach, taking the time evolution of the impact force, which has been previously calculated by the super element solver. The multiple discontinuity method was implemented in ColFOWT project, and the displacement, velocity, and acceleration of the nacelle were confronted to finite element results, obtained either by using a Patron and Nastran solver with a modal superposition approach on a beam model, but also with finite element result from LS-Dyna explicit simulations. And we can see here the time evolution of the displacement at the center of gravity of the nacelle. So we see that our model correlates almost perfectly with Patron results, but we observe some discrepancy on the response period with LS-Dyna. And this discrepancy is due to the fact that shear effects are accounted for in LS-Dyna calculation, but not in our model, because for the moment we have considered only the Euler-Bernoulli theory. But we can, of course, extend the model to Timoshenko beams and take into account shear effect on the rotation inertia. If we look at the acceleration time history just after the impact, we can see that discrepancies of the present model with LS-Dyna and Patron result do not exceed 9%. The module which calculates the acceleration at the top of the wind turbine is today under validation for floating structures. And in the same way, the spiral-like wind turbine is split into several beams, macro elements, with different sections and mass. And the first results show that the beam discontinuity approach allows to rapidly and accurately calculate the model characteristics of the structures. And here again, the discrepancy with finite element simulations for the natural frequencies and mode shapes does not exceed 8%. For the concrete floaters, the first step has been to set up numerical models in LS-Dyna. So we performed simulation of impact of a rigid striker against reinforced concrete slabs. And the reliability of the proposed behavior laws have been checked by comparison with experimental results extracted from the literature. Then the elastic plastic force displacement relationships for the reinforced concrete slab has been built by combining the moments found from the cross-sectional analysis with solution retrieved from classical plate theory and plastic limit analysis for different boundary conditions. The developed subroutine has been compared with detailed nonlinear finite element simulations, and also with experimental tests retrieved from the literature. Regarding the ship now, the deformability of the striking ship has also been considered, and here a striking bulb, for example, is decomposed into several L and T sections, and the crushing resistance is calculated from analytical expressions proposed by Jürgen Amdahl from NTNU. Again, the force displacement curve obtained analytically has been confronted to detailed finite element simulations. Okay, now the overall ColFOWT superelement solver may be represented by the following chart. In the first step, the striking bow and the struck wind turbine are split into elementary components. And then at each time step, the penetration of each impacted superelement is estimated geometrically. And in a third step, the contact force is calculated by considering either a rigid ship impacting a deformable wind turbine or a deformable ship striking a rigid wind turbine. In the fourth step, the mCol solver is called to update the position and the velocity of both the striking ship and the wind turbine, taking into account the hydrodynamic forces that act on the immersed parts of the structures. And the program stops when the struck wind turbines comes off the striking ship. So you can see here in the detailed coupling algorithm that at each time step, in fact, the superelement solver transfers the contact force, Fc, and the mooring resistance force, Fm, to the mCol solver. And mCol solves the equation of motion at the center of gravity of both the ship and the wind turbine by considering the water-added mass, hydrostatic restraining forces, as well as wave radiation and drag damping forces. And the new position and rotation of the center of gravity of the ship and the wind turbine are transferred back to the superelement solver for the next time step. So the proposed coupled model has been confronted to LS-Dyna mCol finite element simulation because mCol also has been integrated in LS-Dyna finite element solver. And you can see here the first results we obtained for a rigid impactor. You can see that we have a quite nice correlation either for the energies or for the contact force. And we have regarding the final penetration into the floating offshore wind turbine, a discrepancy of less than 1%. If we consider a deformable impactor now, that is a 2,000 tons offshore supply vessel with a velocity of 1 meter per second, that is around 2 knots. We can see also that we obtained a good correlation between the contact force calculated by the analytical program on finite elements solver. And regarding the penetration is around, the discrepancy is around 10% for the wind turbine and around 80% for the deformable bulb. And finally, regarding the computation time, you can see that for the damage analysis, that is the crushing of the different superelements, one simulation with ColFOWT program is around 2 minutes, 25 seconds. while a simulation, one simulation over several seconds, physical seconds, in fact, is around 14 hours with LS Dyna MCOL. Regarding the calculation of accelerations, with the ColFOWT program, we can assess an acceleration in less than 2 minutes. The main time concerns the eigen solution. In fact, that is a calculation of natural frequencies on mode shapes. But with an explicit calculation using LS Dyna, we need around 20 hours with a model based on shell elements. So to conclude my presentation, in the ColFOWT project, we have developed a super element solver for ship floating offshore wind turbine collision damage analysis. And the damage of the wind turbine on the striking ship can be very rapidly assessed by this program. And the tool at the moment considers both spar-like metallic floaters, but also float-gen-like reinforced concrete floaters. Acceleration at the rotor nacelle assembly is accurately calculated, and we continue the work at the moment to include solution for low energy impacts. The work package 2 of the project is still in preparation, where we will perform some drop tests with rigid and deformable semi-spheres against reinforced concrete beams in order to validate our super elements involving reinforced concrete behavior laws. Thank you very much for your attention.
Okay, thank you, Hervé, for this very nice presentation and all the results. Sounds very interesting. We got several questions coming in. Let me share my screen again. So for the questions, we got the first one here about what are the existing collision analysis tools for fixed offshore wind turbines, and have you considered adapting them to floating offshore wind instead of developing a new solver?
Yes, in fact, we started from our ship-ship collision tools, but we know that there are some, for example, there is one software which has been developed also in Trondheim by Professor Jørgen Amdahl, which is called OSFOS. But at the moment, at the beginning of the project, OSFOS was considering only fixed offshore wind turbines, that it was developed for oil and gas industry. And we already had the MCOL fluid solver, so we decided to enhance, to improve, to enhance the formulation which have been included in OSFOS software. And especially in order to accurately take into account the crushing, the local crushing of the sections, as well as rear part buckling of the monopiles or the tower or the floating structure. So in fact, OSFOS can perform some calculations that are performed in ColFOWT, but not all, in fact. So we can say that ColFOWT project is like an improvement of USFOS solver, in knowing that USFOS solver is a very nice solver, which now also can take into account floating structures.
Okay, thank you. I guess it was quite complete. Yes, we got a question here. How can we explain the important gap? So time divided by 500 of computation time between ColFOWT simulation and Dyna simulation.
So in ColFOWT simulations, to calculate the resistant force on dissipated energy, we use analytical formulations, which are calculated in a few milliseconds. In a Dyna finite element model, we solve an explicit integration scheme after meshing all the structures, that is the striking ship and the struck floating wind turbine in finite elements, and we have to use a refined mesh in order to tackle all the deformation modes, the plastic deformation modes. So that's why in the finite element simulations, using very small finite elements to capture the different crushing mechanisms, we obtain very small integration time steps, which lead to very huge computation times in Dyna simulations. That's why we have around 10 up to 20 hours of simulations with Dyna for 5 to up to 10 seconds of simulations, and less than 2 minutes because we only solve analytical expressions with the ColFOWT project.
Okay, thank you. So next one is about the validation. So does the super element model and or the coupled model with FEA has been validated with experimental tests and measurements? And if not, is it planned to do so?
For the moment, what we did is that we made a comparison with experiments for individual super elements, that is a cylindrical super element for the tower, but also for the ship bows, for example. But you're right, we did not make any comparison against experimental tests for the coupled super element and MCOL program, because we do not have such kind of experimental tests at the moment. That is, to our knowledge, there have not been any experimental test involving a ship, a small scale ship with a floating wind turbine at the moment. So this will be perhaps a future project to develop some experimental test in a test tank, for example, in order to see if the rolling movements or the pitch movements of the structures is correctly simulated.
Okay, thank you. So this is not playing during this project, but that could be the subject of a future one, yeah?
Exactly, yes.
Okay, thank you. So I'll continue. And next one is about are collision analysis needed to be included in the risk analysis for an offshore wind project bid? So I guess, does the developer actually needs to include this kind of risks analysis when they apply for a project?
So we know that for the moment, from the Ministry of Transportation in France, we know that when a shipyard or yard will build some new wind turbines, they will have to demonstrate the different consequences of a ship collision against these wind turbines. For fixed wind turbines, but also for floating wind turbines. And one important thing is also to know how to locate the rescue ships with respect to the wind farms. That is, in case of collision, or in case of propulsion failure of a ship, for example, we must know what will be the consequences of a collision against a wind turbine. And for the moment, the regulation just ask the developers to demonstrate that the collision will not lead to an important consequence on the ship. For example, the failure of the weather deck, of the tanks, etc. It's also requested to check if the mooring lines will resist or not in case of collisions. And of course, we must demonstrate the stability of the wind turbine, the floating wind turbine after collision damage. So I cannot say more about the regulation because I think that the regulation is changing also now, and as the floating wind parks are quite new, the regulation is evaluating also regarding this.
Okay, thank you. So we got a question here from Luc Mouton. I understand that yet you have not performed complete simulation using concrete floater, but yet comparison between super elements and lab beam tests.
No, in fact, we have compared our simulations, analytical simulations, against finite element simulations. Okay.
Yes.
But we would like also to perform some tests in order to better validate the numerical simulations on the, more exactly, the behavior laws which are used in the numerical simulations, because we are not completely confident with the numerical simulations at the moment, in fact, because the finite element codes provides a lot of behavior laws, different behavior laws, taking into account different damage loads. We can compare with some slab experiments, but we would like also to enhance, to improve the test, to improve the check of the numerical simulations, to be sure that they can be considered as a reference. But for the moment, taking into account the laws we have in the finite element codes, we can say that we have good correlation between the super element program, which is coupled with a fluid MCOL solver, and finite element simulations. But since the beginning, some experimental tests were included in the ColFOWT project, and we will perform them because we want to have more experimental results regarding the reinforced concrete.
Okay, and so these tests are planned during the next year.
The next month, yes.
The next month. Okay, thank you, Hervé. So next question from Alexis Darquin. Spar and reinforced concrete floatgen type floaters are not likely to be the main floaters types launched in the upcoming years. What about a solver for semi-sub steel type floaters?
Yes, this is a very good question. And we have identified this structure. So in fact, we are as I said, we are working with University of Liège and University of Trondheim. And we just started with University of Liège in September, last September. We just started a new PhD thesis with the aim to develop super element for semi-submersible floaters. So this will not be performed in the framework of ColFOWT project, but this will be performed in the framework of a new PhD thesis from a Belgium research project granted by the Research Fund of Belgium. So yes, this will be the next step to develop, to enhance, to improve the analytical solver to semi-submersible floaters.
Okay, and so this new type of floater is planned to be included in the numerical solver.
Exactly. Exactly.
Okay, thank you. Next question. As BV, so Bureau Veritas, is member of the project, will the tool be validated to include this collision analysis in rules and guidelines?
This would be my hope, in fact, of course, but for the moment, I cannot speak on behalf of BV, so I don't know. I know that BV is very interested by this development in order to have a second tool and to be able to check the calculations that are made by the design offices using finite elements, for example. And also, what I can say is that in the framework of your European project, which is called FLARE, that is a flooding accident response, a proposal will be made to IMO, that is International Maritime Organization, to take into account the crashworthiness of impacted structures in damage stability analysis of ships. So the regulation is changing now, and the regulation will change in the next year regarding damage stability analysis of ships. So I imagine that several years after, we could have also changes by IMO for the wind farms.
Regarding, so for example, floating structure or
exactly
structure.
So on one advantage of this kind of tools is that a complete damage stability analysis can be performed, because this stability analysis involves, as I said, hundreds or thousands of different collision scenarios.
Okay, so and next, so we got a question from Stéphane Pabeuf, so from Bureau Veritas, actually. Thank you, Hervé, for the nice presentation. And what are the next steps, improvement expected?
So, as I said, for the next step, we are working on including elastic response in order to tackle low energy impacts. And as I just said, we will enhance the solver to semi-submersible. And my dream would be also to mount a new research project in order to perform some experiments in towing tanks to validate all the developments, that is to be sure that the large rotational movements of the impacted wind turbines are correctly simulated. So this will be the next steps. And another step would be to, I would say, to apply what has been done in the framework of the FLARE project, that is to study, to investigate what would be typical scenarios of impact and to have a database extracted from risk collision simulations, that is knowing the different ships navigating in the neighborhood of the parks, knowing their velocities, knowing their direction and so on, and to be able to derive the possible scenarios of collision. So when we will have the possible scenario, we can couple the possible scenarios with ColFOWT project to perform a complete risk damage analysis.
Okay. Okay, I guess it is clear. So we don't have further questions at the moment. So I guess we can thank you, Hervé, for this nice presentation.
Thank you very much for listening.
And for answering the question. I guess it was quite clear for all the question. And please, you can contact us, me at WEAMEC and Hervé, if you need more information about the project, or if you want like to collaborate with the consortium, and if you would like to be involved or in future collaborative project, or even to use actually the development made in ColFOWT. So it's no time for me to talk about what's next. So for the moment, we don't have a proper project confirmed for the next dates, but we do have 2 dates for the next WEAMEC webinar. So that will be on 24th of March and then on 28th of April. So you can save the date on your agendas, and we keep you informed of what is going to be the projects to be presented. And you will receive, as usual, a link to the synthesis of today's webinar, and you will have the video link also. So that should be done in a few days. So as all the webinars of WEAMEC, so as I said at the beginning, it's going to be stored on our YouTube channel. So please feel free to share this content if you think about colleagues that may be interested about this presentation. You can subscribe again to our WEAMEC newsletter to keep informed about latest WEAMEC activities, but also widely about offshore renewable news and activities. So this is on our website, and you can follow us on the social media accounts from Twitter, LinkedIn, and again, the YouTube channel. So I guess it's now for me to thank you for your participation. Thank you again, Hervé. And
thank you very much.
We see you soon for our next webinar.
Bye-bye. Thank you.
Goodbye.